So let's see. I mean, when back at the end of the chapter 4, we had the antiderivative. That is the function whose derivative was the given exercise. All right. And well, all we do is integrate or find the antiderivative of little f, turn it into big F plus c. Because again, for example, when we integrate x dx equals x squared over 2. However, well, so that's the function whose derivative equals to x. But the thing is, that's not the only possibility. You can have x squared over 2 plus 5, that the derivative of this is x. You can also have x squared over 2 minus 9. The derivative is also x. So in this case, well, how do we make sure that we're not missing out anything? Well, so just add a plus c. That plus c represents whatever constant, because I mean the derivative of a constant is 0 ultimately, right? And so depending on the professor that you took in the future for Cal 2, Cal 3, or even any advanced mathematics or other courses, you will use different ways or different words for this operation. Number one, integrate, or actually other textbooks or resources online that you use to enhance your studies. For example, another way to say this is find the antiderivative. It's the same thing. Regardless of the textbook, the resource online, the instructor, it's the same thing, all right? And another thing here, and this is very important, these two signs, the integral sign, always go with the dx. For example, the integral of sine x, the integral of square root of x, the integral of e to the x plus 1. Well, I mean, this is meaningless if we don't write down the dx. It's important to write down these dx's. That's part of the criteria for grading in any quiz, exam. If you're missing the dx, well, technically, the reason why this is technically wrong, it's because, well, here we're integrating the function sine with respect to x. We need to specify the variable in which we are integrating. So, because later in calculus 3, when you get to functions of multiple variables, you have a function x squared y cubed plus cosine of y z in this case. All right? But I mean, that doesn't mean anything if we don't specify with respect which variable we're integrating to. So in this case, well, this is an integral maybe with respect z, for example, and we need to be very specific of that. And of course, well, later also in calculus 3, multivariable calculus, you will have the same integral. Well, let me write down the integrand first. X squared, y squared, or cube rather, plus cosine yz, and that's, in this case, it's going to be a triple integral, and that you'll have to do the process 3 times. The first time, well, depending on the order, typically we go in descending order in the alphabet. So we integrate first with respect to z, then with respect to y, and in the end we integrate with respect to x. So that's why having this dx attached to the function or to the integral is very important, because that actually tells us, with respect to what, like when you're writing a program in whatever language, whatever programming language, C, Python, MATLAB, whatever, you declare a variable, and that variable could be an integer, a float, a decimal, whatever, or simply not even a number, actually a word, or another symbol. But in that case, it specified what it is. In this same situation, we do the same thing with integrals, when you should be very specific with respect what are we integrating, all right? And again, we cannot have one without the other. These two go together, all right? So, now another very important piece of information, and this is a part of a pattern that you might have figured out at this point. Number one, a definite integral, that is an integral that contains limits a from a to b. The result of that is it's just another number. However, an indefinite integral, it's another function, or rather a family of functions, because recall that when we integrate or when we find an antiderivative either way, we write down the result and we add the constancy. Again, that constancy will depend on the condition that we're given or that is set to find the particular member of a family of functions. But in general, we just the integral or the antiderivative. In more in particular, the indefinite integral gives us the picture of the family of functions, if we will. All right. Table of integrals. Well, this is the very basic table of integrals. I mean, these are exact same formulas that we discussed at the end of the section. What was that? 4.9 or 4.8? I can't remember exactly. But we didn't have that integral sign. We didn't have that plus c. All we did is simply write the functions whose derivative were the things on the right hand side. I mean, on the left hand side rather. But this time we are writing this using the integral notation, and it's exactly the same thing. You know, the general power rule: add 1 to the exponent, divide by that new exponent. The integral of sine is negative cosine. The integral of where's cosine? Never mind, it's not here for whatever reason. The integral of, let me write it down. I think it would be worth to have it. The integral of cosine x dx equals sine x plus c. All right. Well, again, this is just a little sample of what table of integrals are. Well, actually, there are books of integration formulas, books that are like thousands of pages of just formulas. Of course, I mean, those books are used typically for when you're doing some research or something and you don't want to compute the integral by whatever method. Well, speaking of such, those integrals, many of those big integral formulas come from the methods of integration that we will discuss next semester in calculus 2, such as integration by parts, trigonometric integration, trigonometric substitution, partial fractions, and other weird and crazy substitutions. But for now, let's go with the basic ones. And again, these are basically the reverse of finding the derivatives. All right. So how about we just do some examples? Well, so let's integrate or find the antiderivatives of these functions right here. My advice, I mean, because we're barely learning this. Most of you are looking at this for the first time. If you have done this before, well, you already have an idea. But my advice is, number one, write it in terms of two integrals. That's 10 x to the fourth dx. All right. Recall that the integral sign always go with the dx symbol minus the integral of 2 secant squared x dx. Essentially, we are distributing the integral symbol to both terms, and we are distributing the differential symbol to both terms. That's essentially what we're doing. All right, so, well, another thing that I would advise you guys to do is all these constant factors, take them outside of the integral. That is 10 times the integral of x to the fourth with respect x minus 2 times the integral secant squared x dx. All right? And this, so you can easily focus on what remains inside of the integral. That is called the integrand. In this case, this first integrand is the x to the fourth power, and this integrand right here is secant to the second power. And well, for now we're gonna have integral for which we're gonna have direct formulas to just go through them. Well, here we have the form x to the n, and here we have the integral of secant squared. Well, secant squared comes from differentiating which function. Well, we no longer have to think that way. Again, at the beginning, when we first touched base on antiderivative, the way we were describing is, oh, what's the function whose derivative is x to the 4? What's the function whose derivative is secant squared? No, no longer. Just refer to the table of integrals. Well, we have something of the form x to the n, add 1 to the exponent, and divide by that new exponent you get. And the integral of secant squared is simply tangent x. That's all we do. The moment we replace with those new results, we no longer write the integral symbol or the dx. So that is 10 times x to the 4 plus 1 over 4 plus 1 minus 2 times tangent x, and here is where we add the plus c. So no more integral symbol, no more dx or differential symbol. That's the antiderivative or the integral. All we have to do now is simplify this to lowest term. So that's a 10x to the 5th power over 5 minus 2 tangent x plus c. And well, just make sure to reduce all the fractions whenever possible, because when you're working on the homework on WebAssign or any other system that you use, well, here we use WebAssign. Typically, they're very picky, and they say something like, "Oh, although your answer is correct, it's not written in the most simplified form." So just make sure to do that. So that's 10 over 5. That's 2x to the 5th minus 2 times tangent x plus c. And that's final answer. That's what it is. All right. Letter B. For letter B, we're going to do something similar. So number 1, we have the integral of a function comprised by 1, 2, 3, 4 terms right here. 4 terms with respect to x. Again, my advice, write this in terms of as many integrals as terms that we have. Of course, later in the future, as you get a lot of practice with this, you will be able to do this in your head. However, the reason why at the beginning I advise to write every term as its integral, mostly because of its coefficient, and that's going to help us a lot later in the next section when we look at the substitution method, which is going to be a big deal. That's the biggest of the deals here in this class. You'll see. So number 1, that's the integral of 5e to the x with respect to x. Again, we are distributing the integral sign and the differential symbol, minus the integral of 4 to the x dx plus the integral of 3 over x dx plus the integral of 2 dx. All right? So we just distributed the integral symbol and the differential symbol. The next step is if possible, and actually it is for 1, 2, 3 integrals, to get those constant factors outside of the integral. That is 5 e to the x, 5 integral of e to the x dx minus, well, there's really no constant factor over here. That's just 4 to the x dx plus 3 times the integral of dx over x and plus 2 times the integral of dx. All right. Well, the integral of dx, of e to the x, the integral of 4 to the x, well, be careful because here we're integrating 2 exponential functions. One of them is a function e to the x, which is pretty straightforward. I mean, the derivative of e to the x was itself e to the x. So it wouldn't be surprising that its integral will be also itself the same. However, it's not the same when the base of the exponential is a number other than the natural e, the natural exponential e. So in this case, well, also we have the integral of 1 over x And well, this one is straightforward. Let's go back to the table of integrals. So, oops. Number one, we want to integrate e to the x, which is itself. Got it. We want to integrate an exponential function whose base is another number. It's a number other than e. That's going to be, yes, itself, b to the x. However, we need to divide by the natural log of the number which is the base of the natural log. For example, where is that coming from? Well, recall the derivative of f of x. For example, 2 to the x. The derivative is itself 2 to the x, but in this case times ln of 2. So what did we do when it came to differentiating an exponential function of a base other than e? We multiplied by the natural log of the number that matches the base of the exponential function. But now, because we're doing the reverse process, we are integrating, so the reverse of multiplying should be dividing. So that's why we have that in the denominator of the exponential function. All right? What else do we have? Oh, careful with this general power rule. I think it's worth to discuss all this. You'll see why. This one also works for n not equal to -1. What happens if you use, for example, the integral of the x over x, which is really the integral of x to the -1 dx? If you use this formula right here, you will get the following: x to the -1 plus 1 over -1 plus 1. That's going to be x to the 0 power over 0. And well, we have issues with that one, right? We have issues with, so we cannot use, we have its standalone formula for this situation. And that's just because the derivative of natural log is 1 over x, all right? And notice at the same time, the integral of 1 over x, it's not just natural log of x. It's natural log of absolute value of x. Well, let me go through all the details of that. Why do we have these absolute value bars? Number one, okay. So let's consider number one, the function f of x equals 1 over x. The graph of this function, well, looks like this. All right. Notice the domain of this function. The domain is all real numbers. All real numbers except 0. That is, in other words, the domain of the function f of x 1 over x accepts both positive and negative numbers except 0. However, if we think of ln of x, if we think of the function ln of x, the graph looks like this, and we know that the domain of ln of x is just all the set of all positive numbers excluding the 0. Well, but there has to be a way to carry, because these operations, when we go from a function to its derivative, somehow we have to carry the domain of the function that we are integrating. And in this case, the domain of the function that we are integrating, that is 1 over x, it's all real numbers except 0. The domain of this one is only from 0 to infinity, only the positive numbers. Well, what do we do to also carry those negative numbers? Well, put absolute value bars and make the graph like this. All right? That way we can keep the sense of carrying the same domain of the function that we are doing so. That's the reason why we put these absolute value bars. Later, when we discuss the method of substitution, we will discuss cases in which we don't need those absolute value bars, but those will be particular cases, and we will get to those later. In the meantime, let's just go back to the integration here. So that's number one, 5 e to the x minus 4 to the x over ln of 4. plus 3 ln of absolute value of x plus 2x plus c. And we're done over here. I know most of these formulas look like very straightforward, like, oh, change this to that. That's all it is. But I think it's important to look at some of the details and why are we having this little subtlety here and there, because it's going to matter a lot as we move on through this. All right. So for the next example, letter C, the integral from 0 to 2 of 2x cubed minus 6x plus 3 over the square root of 3 over the square root of 1 minus x squared. Well, we have a bunch of things in here. Number one, we have a definite integral, and although this section is about the indefinite integral, well, we're going to do some definite integrals. Really, the objective here is to, in a way, run away from the concept of the antiderivative and really get into the concept of the integral. Use the integral symbol, the differential symbol, etc., etc. But still, okay. Let's write down as 3 integrals. The integral from 0 to 2, 2x cubed dx, minus the integral of 6x dx from 0 to 2, plus the integral of 3 over the square root of 1 minus x squared dx from 0 to 2. All right? So that's the first step you want to do. Number one, distribute the integral symbol along with the limits of integration and distribute the dx symbol. All right. So the next step, again, take out the constants. It's going to be a lot easier. That's 2 times the integral of x cubed from 0 to 3 with respect to x, minus 6 times the integral from 0 to 2 of x with respect to x, plus 3 times the integral from 0 to 2 of dx over the square root of x, over the square root of 1 minus x squared. All right? Well, I already say dx, not... So again, you can say the 2 ways you can read this integral. Number one, the integral of x cubed dx, or the integral of x cubed with respect to x. Again, these are different ways to say the same thing. Right? Let's see. So let's just use the required formulas. General power rule, and let's look for this form, 1 minus x squared in the denominator. Let's see if we have anything in our table of integrals. And it looks like the last one right here. So it's the one that results into arcsine. So that is, and that comes from taking the derivative of arcsine, which is this weird radical in here. All right. So let's just use that result. Actually, there's a little typo here. This one should be an x, not a u. The u thing, however, we're going to use it in the next section when we cover the substitution method, and we're going to do a lot of this just to get you ready for Calc 2, actually. All right, so that's going to be 2 times x to the 3 plus 1 over 3 plus 1 minus 6 times x to the 1 plus 1 over 1 plus 1 plus 3 times sine inverse of x, and the whole thing. So we recall from the fundamental theorem of calculus, once we get to the antiderivative, we write a vertical bar, lower limit, upper limit. And we'll simplify, so that's 2 x to the 4th over 4 plus 6 x squared over 2 plus 3 arcsine or sine inverse, either way. Oops. From 0 to 2. This reduces to 1/2 x to the 4th. Or let me write it the other way, actually, because I'm going to do operations with this. X to the 4 over 2 plus 6 over 2, which is 3x squared. And plus 3. Oh, actually, this is supposed to be minus. And 3 sine inverse of x. I mean, I know right now I'm writing a lot of steps, a lot of symbols, but again, once you get to practice a lot of this, you should be able to pretty much go from here to here actually, to this point. For right now, doing a whole thing. All right, so that's upper limit minus lower limit. So that's 2 to the 4th over 2 minus 3 times 2 squared plus 3 times sine inverse of 2 minus, okay, a freebie here in this case is that number one, observe what's going to happen when you substitute the lower limit of x equals 0 to all the antiderivatives, the terms in the antiderivative or the integral. This term is going to get zeroed out. This term is also going to get zeroed out. And this sine inverse of 0, which in other words is asking us for the angle whose sine equals 0 also happen to be 0. So in this situation, it's fine to just do a big 0. That's fine. That way you don't write that whole thing evaluating at 0. However, if you still prefer to write every single term and evaluating at 0, that's up to you. That's fine. But that's kind of a freebie that, you know, and it's okay just to save some time on your work, all right? And then, well, let's simplify what we have here. So that's 2 to the 4th power, that's a 16. 16 over 2, that's 8. 2 squared, which is 4. Times 3, that's 12, negative 12. And, well, sine inverse of 2. In other words, they're asking us for the angle whose sine equals to 2. Because in this case, we don't have this is not a value that it's in the you know, in the unit circle. We just leave it as sine inverse of 2. All right, let's just leave it like that symbolically. And 8 minus 12, that's simply negative 4 plus 3 sine inverse of 2. Let's just leave it like this. All right. Otherwise, if we had something like sine inverse of a half, well, that's I believe it's 30 degrees or pi over 6, or sine inverse of 1, that's the 45-degree angle, right? That's pi over 4. But in the meantime, for values like this, just leave it like that. Okay. Let's look at one more example here. So that's the integral from 0 to 1 of 3 over x squared plus 1 with respect x. So what I would do first is take out the 3 outside of the integral and leave the form x squared plus 1 and write down the limits from 0 to 1. And let's see if we have a form that can help us get the integral of this. Well, let's go back to the integral table in the previous page real quick. And it looks like we have something actually. We have this form, the integral. I mean, I know you could argue, well, but that's in the reverse order, but that doesn't matter. Actually, when you look at this form of integral, you can see it as a form 1 plus x squared or x squared plus 1. It doesn't matter because it's addition of terms. It doesn't matter. And in this case, this is the function whose derivative is 1 over 1 plus x squared. That is the arctangent function or inverse tangent function. Another way to denote this, let's recall. This is arctangent, and this is also arcsine. All right, even the arc notation or the negative 1 power. Whoa, actually careful. This negative 1 is not an exponent. It's just to denote that it's the inverse function, because a very common mistake is to say this, that tangent to the first power, to the negative 1 rather, which looks like a power, it's the same thing as 1 over tangent of x. And this is not true. This would be the reciprocal, and in this case we're not talking about reciprocal functions, we're talking about inverse functions. All right, that being said, let's see. So this is whoops, This is going to be 3 times tangent inverse of x evaluated between 0 and 1. All right? And again, fundamental theorem. So this is 3 times tangent inverse of 1 minus 3 times tangent inverse of 0. And well, in this case, okay, let's evaluate this inverse tangent. In this case, it's possible to evaluate them because these are values that are in the common angles that we know from the unit circle, or the representative right triangles, the 30, 45, 60 degree angles, all right? Well, in this case, they're asking us for the angle whose tangent is 1. Any ideas of what angle is that? Any ideas? Yes. Pi over 4. If you're not sure about it, well, how about write this tangent of 1? Write it as 1 over 1 because, well, trigonometric functions typically rely on quotients between two quantities in which one of those values in the quotient it's either the length of the sides or the length of one side and the hypotenuse. And well, tangent by definition is opposite over adjacent, opposite over adjacent. If this is a reference angle, this is square root of 2, and indeed that corresponds to the 45 degree angle. Yes? Also 5 pi over 4. However, we need to be careful with the 5 pi over 4 because that may not be within the range of the inverse tangent function. All right? Actually, the range of the inverse tangent function, that's a good question. Thanks for pointing that out. It's the domain of that function is just the first and the fourth quadrant. So in this case, it's only the pi over 4. So that's going to be 3 times pi over 4 minus 3 times the angle whose tangent equals to 0, and that's simply 0. And final answer, 3 pi over 4. All right. Okay, so I'm going to do one more and we call it a day because, well, what's next? For the next one, yes, verifying the following. Yeah, I think we can do that next time. I'm going to do one more. Okay, so here is where things are going to get a little crazy. Well, because unfortunately in this situation we don't have a direct formula to integrate this. However, those of you who have taken calculus in high school, you may have seen the method of substitution already, and you can already tell that this one can be evaluated using the method of substitution. But right now in this class, we don't know what that is, right? No, let's pretend we don't know that. So, in this case, we're going to use trigonometric identities in this case. So, number 1, I'm going to rewrite this sine square in the denominator as, well, integral of cosine theta over sine theta times itself. All right? And I'm going to group this cosine with this sine, and I'm going to use a trigonometric identity here. So what do we get when we divide cosine theta and sine theta? Which one is it? Tangent theta. I think tangent theta is the other one. It's sine over cosine. So this one, which is the reciprocal, has to be cotangent, right? Cotangent. So cotangent theta, well, it's still over sine. And I'm going to move this sine theta to the numerator using another identity. So what's the result of finding the reciprocal of sine? What's that? Anyone? The reciprocal of sine? Cosecant. Cosecant. Well, we have a form for cosecant cotangent because that's the derivative of, let's find out. It's right here. The integral of cosecant cotangent becomes negative cosecant. And that's our final result. Right?